we are actually where we are actually the VLS engineers performs logics, try to implement logics. So they are try to solve the problems, right? So for that a tool is necessary to make the process fast, to make the completion of the project easily. So first of all, we everything as a VLS engineer we will test virtually. Then only we will go for the physical implementation. In olden days, so the transistor size was very less. Actually, it's very more, and actually the complexity of the circuit also more. At that time, there are no tools, software tools, but nowadays everything is processed into virtual world. So we are actually developing the logics in the tool, and automatically the tool will take the control of developing into the chip. So before going to chip, we have to convert to the whatever the logic we developed, that should be converted to the gate level netlist. So gate level netlist is nothing but the logic we written, that's okay, but that should convert it to the gates first, like AND or whatever the mux combinations counters that, and after that it will go to the transistor level. Then after the physical implementation will take place using other tools. But as a simulator, as an RTL engineer, we should aware of simulation tools. Like we have so many tools. For example, we have QuestaSim from Mentor Graphics, Xilinx, Vivado from Xilinx, AMD, and even a paid tool called Synopsys VCS tool. This and all we have in the physical, like whatever the fields we are working, right, real life fields. These and all the tools we have. So we will go slowly. What's actually tool will perform? What's the process of using the tool? Let me start my presentation. See, today we are going to discuss about how to actually implement the combination logics, RTL design and test bench. So everyone know what's actually the Verilog code. They know the basics. So before going to the basics, first of all we have to understand what's actually design and what's actually test benches. See, this is an RTL block. RTL block is nothing but whatever the logic we written, that should synthesize every construct whatever we are using, every line of code whatever we are using, that should be synthesized. And coming to the test bench, test bench is nothing but we are going to give the inputs. Let's take, so you developed, let's take you developed some mug. Okay, so let's take this mug as RTL code. So for using this mug, for building this mug, what we need? Let's take a plastic mug. So we need plastic material, then the mounted materials, then the instruments for used for everything. So the material whatever you are using, and we are implementing that using RTL code. For testing that RTL code, we need another thing, right? That's actually test bench. For let's take how this mug can be tested. We can heat this, we can break this, like this every time. We will like our wish. We can test this mug anyway by breaking, by heating, like that. So that and all can be given as a TB. So we will develop the code, then we will provide the inputs. Like that, our design will be verified using the test bench. So two types of code we are going to learn. So today in this class we are going to learn 4-bit ALU design using Vivado. RTL design we are going to implement. So we are going to aware of what is a linear test bench, and we are going to aware of what is a task based test bench. See, today's agenda is our we are going to see what's actually ALU RTL design looks like. So what is the approach of what is the approach of a linear test bench, task based verification and simulation flow of Vivado tool, and combination logic concepts. So in this combination logics we have no clocks at all. So we are purely working on combination circuits, right? So here there is no necessity of using clock. So everything based on just what are the inputs it will give, based on the logic the output will be produced. So no clock is there, no memory elements are there in this combination logics, and using this always at the right start. So before that, before class we are aware of assign statements. So assign is purely for what? It actually drives the inputs continuously for wire data types. Coming to the always block, it's also actually used for implementing combinational logics. See, we are actually learning about combinational logics. Combinational logic we will use always, @ we will use. Then we will inside always, if there are multiple statements means we should use begin end. Okay, there are so many statements. So the statements are nothing but your own logic. Let's take y equals to a plus b, like that. So here if you are using y is an output, right? So if you are declaring y means that should be rect data type. So always block only allows rect data type to be assigned left side, but right hand may be y data type or rect data type in always block. So this is useful for this. If you synthesize this means this code, it will implement to the real hardware, like what you call adder circuits. Like this we are implementing this combinational circuits. Coming to the sequential circuits, just give an idea, we will more learn on next class. So always @ pause edge or negate of clock, we should use this syntax. So if you are implementing, if you are using the sensitivity list, so if whatever we are providing inside these brackets, we are call it as sensitivity list. Okay, so begin end. If before in this inside block, we will use y equals to a and b. Let's take. So if you are implementing sequential circuits, we will use this assignment. So see, less than or equal to, this we will call it as non-blocking assignments, and equal to we will call it as blocking assignments. So combinational circuits follows blocking assignments, whereas sequential circuit follows non-blocking assignments. So for example of combinations, we have ALUs, mugs, decoders. So many sequential logics we have. So see, our 4-bit ALU specifications, inputs what we are taking 4-bit input, 2, and actually a selection line for selecting multiple operation. What actually an ALU do? See, let's take it's an ALU. You know, right, basics. Based on inputs, we are giving A inputs and we are giving selection line. So selection line, based on selection line, it may perform so many operations, like it may produce adding, it may produce logical and so bitwise, and we can use logical and we can use reduction operators like reduction operators, you know, right, XOR. So we will have so many operations. Based on selection input, it will do the operations and will give the outputs like carry, 0, sign, or parity. So these are all the operation ALU will perform. So based on the selection line, it will select this operation, and based on that operation, it will produce these type of outputs. And simply, so RTL coding best practice. So how you to use the best practice? Use case statements for operation selection. So why case only? So we will get out. Temporary 5-bit register for carrying handle. So we are using 5-bit registers, and we are assigning flags after result calculation. So we are performing some operation and we are generating the output. So we are assigning that result to the flags to know the status of the registers. So cover all cases to avoid latches. See, you know, case, right? Case statements. Cases actually work with these. Here we have to give the case, what are the inputs that is going to change. So based on that case statement, here we have case items. Based on case items, we are having the operations. So simply it acts like what? Mux. Based on, let's take the left hand side part as selection. Based on that selection, we are going to perform the right hand side operations. So just go through the case statement once again. So here, ensure synthesizable design. RTL coding will ensure definitely synthesizable design. Whenever we are working as RTL engineer, we are focused to only whatever the constructs we are using, that should be synthesized. So today your assignment is like just go through whatever the synthesizable constructs in Verilog. Just go to whatever the synthesizable constructs in the Verilog. Please note it down. So there are so many constructs we have in Verilog which are synthesized, and go through non-synthesizable also. So based on that synthesizable, non-synthesizable, we will decide to implement the pure RTL which is synthesizable. Here see. So first of all, what is a linear test bench? So direct input stimulus. Let's take what we are going to write an simple operation like A and B. So for this, directly we will implement. Directly we will assign 0 or 1. Directly we can do in the coding. That's actually a linear test bench. So simple, this simple linear test bench look very simple, but the lines of code is more. Only the difference between simple linear test bench. So manual value assignments, actually we have to assign the manually we have to assign each value. The code length is very more, so it looks like verbose. That's why we are going to another test bench types. So simple delay observations, you can add simple delays like hashtag 10. This is simple of this is symbol used for giving delays, and we have $display statements, and which are used for debugging purpose. Easy to understand for beginners. So as a beginner we will understand this linear test bench, but in the industry we are going for self-checking test bench, and we are going for SV test bench, and we are going for EVM test bench. There are so many test bench types, but right now as a fresher we have to learn what is actually linear test bench is. See, the task based test bench and functional DB. So here second type is of what? Task based test bench. So reusable task for input applications. So functions for expected result compilation. So here we can use tasks, you can use functions in our test bench to make our code more reusable. Okay, and here we will use loops like for loops. If you are a bit of C programming, we can use for loops. We can use so many loops. We can use always. Always is also a type of loop. It's actually continuously it will iterate based on the condition we provide in the sensitivity list. And there is actually other loop called forever. There are so many loops. So automated pass fail checking. So we can check in test bench itself without checking the simulation. Without checking simulation, we can directly check our design is working properly or not using these functions. So that you are going to see in the code which I am going to show. So here Vivado simulation flow. So in every interview they will ask whatever the tool you learn it perfectly. So let's take we are having Vivado. Okay, right. So what's actually the tool is following? They will ask a basic flow, like basic question like please explain the tool flow. So what the actually tool will start and how actually the tool will end. So here we are going to create RTL project. So first of all we have to add the RTL file and test bench files. First step. Then we have to set the test bench and top module. So we have to set the test bench as top module. Then we have to perform the simulation. Then we have to analyze the waveform. This is the flow of the tool. Actually for complex operations we have so many other steps also, but as a basic code we have to do these basic steps for understanding our tool flow. And see, so these are the interview questions, so please note it down. So discussions. So why we are going for the always star, not assign? Why we are using always? So why we are going always means for simple designs we can use assign statement. For if you are working with complex designs and we are working with more number of codes in the RTL design, we will go for always block. And why we use 5-bit temporary register? Just after explaining the RTL code, just go through it. What happens if you use default is missing? So case statement I said, right? Case, end case. In between we have case items and case statements. So what if you don't use default in the case statement? What happens? Just go through it. Just do research on case items. And linear test bench versus task based test bench. What actually? Which is useful more? At what time we have to use task based and linear? Just go through once. And in this design fully synthesizable. So whatever the RTL we are writing and we are implementing, is it synthesizable? Every construct is synthesizable or not? We have to be aware of. If you use non-synthesizable means definitely that code will be rejected. Even sometimes it may lead to your the company may be not good enough to make you to give salary. Sometimes if you use non-synthesizable constructs means definitely they will think like this guy is not able to have a basics also. why we have to give the salary. So we have to learn everything. So we have to learn what are the synthesizable constructs, and we have to know what are the non-synthesizable constructs. And this is the basic thing of for combination circuits. So now we will perform the tool form. We will go for tool execution for ALU. See, let me open. I think most of you guys, I hope you installed Vivado tool. So this is the icon, right? So just double click on it. The tool will invoke. Sorry guys, the screen is not shared, you are saying. Okay, just go through the explanation in the LMS access. So we will go for tool explanation. So we will just go to the theory. We will give the theory in LMS, right? Just go to the theory. So I think hope my screen is visible to all now. Sorry guys, I'm unable to catch your point. So thank you. All right. You can go through the LMS for theory. We will perform the tool. So this is the icon of Vivado, what you installed here. So just double click on it. The tool will invoke here. So the tool will look like this. So here there are so many operations. So you have so many options like create project, open project. So you will create a new project. So here just give whatever the project you want. So I am giving ALU. So we are going to learn ALU right today. So ALU 1 to 3. And so we are going to implement RTL project. So that should be selected. We have to check. Okay. So this like this it will open next. So we have to create two files, I said, right? First one is RTL file, and second thing is test bench file. So here you have to add your files. So if you previously created any files, you can add your files. I actually not created anything. Now I am going for create file. So here I am going to give ALU RTL. Just press OK. So it will be added. So it is in this file we are going to both synthesis as well as simulation also. So just make it correct. And second file is we are going to add ALU TV. So just press OK. So it's actually added. Here we are only giving for only simulation. So our TB is only for simulation purpose, not for synthesizable. It's only for giving inputs to the TB. It's going inputs to the RTL. So just press next, and after that, so they are saying add any constraints. So actually it's complex operation. So right now we don't have any timing constraint. Just we are understanding how the actual code works. No need of adding this one. Next, press on next. So here there are so many FPGAs. So see, while you are working on Xilinx ISE, like old versions, there are only particular FPGA boards we have, like Spartan 6 like that. But here we have so many boards, FPGA boards we are going to have. So here select board options and go last, and you will get this board. You can select any board, no problem. I am selecting this board. And after completion, just finish. Click on finish. So the interface will look like this. Then we are the pop-up came. So for TB and RTL, just press on OK and press on yes. So it will reload. So see here, just we observe here only. Our main concentration should be here, sources and simulation purpose. So here we are going to expand this one. Here we have our RTL file. Double click on it. So you will get right side here. The file is right now is empty, right? Now if you want to write the logic, write here. If you have any previous files, you can add there only, at starting only. Right now I have file. I written my RTL code, everything in the notepad. I am going to copy the file. I code. This is the RTL code. I will explain. So just paste the RTL code and save it. So it's updating. Just wait for a while. So it's updated. So our RTL file is updated with a module name. This is the module name we are using, combination ALU. That with our module name it will be updated. Now we have to go for simulation. So the RTL is everything synthesizable. Like that constructs, every construct is written in such a way that everything is synthesizable. Next we have to go for simulation sources here. So here sim1. Here we have what? Our RTL TB file. So double click on it. See, after expanding this non-module files, we have our RTB file. So double click on it. So here nothing is there. I also have TB file. So first I will copy the linear test bench. So this is the linear test bench. Everything is very simplified version. Okay, after getting this, save it. So now we will go for RTL file. So it's updating, wait for a while. And the tip is like you have to check the hierarchy. See, here the TB should come at top. Inside TB we are under TB, we will get our DUT. Like this only that should be. Then only our simulation will work. So if TB is above, your RTL is above and TB is down means, so it will give unknowns and high impedances in the simulation. So just make it a note. So we will explore RTL file. So RTL is like this. So whatever the design I showed before, like it looks like what? So this is ALU, right? So these are the inputs, this is the selection line, and these are all the outputs, only 4 outputs. Inside that there are so many operations are there, like addition, subtraction, and or XNOR, like this. So for that we have to define, first of all we have to define inputs and outputs, right? So this see. So module, we have to give a name. Inside that module we have a port list. So these are the ports, we have input ports, output ports. So see, why we are using reg? Here we are using always blocks, right? That's why we are using registers. So just declaring as register, it won't implement a flip-flops. If you use that register inside always block, then only it will implement to the flip-flops for storing the 1-bit elements or 2-bit, whatever it may be. Here we have taking extra register temp for helping purpose. See, this is the combinational logic, and inside we have case also. I said right, case can be used as multiple selections. So based on the selection, here we have, this is the selection. Based on selection value, if you give the selection value as 011, that will perform what? It's an OR operation will be performed and output will be assigned to Y. So like this we will write the case statements. And I said, of course, if we should write default. So if you miss this default, it will invoke latches. So we should not remember, we should not forget to write default. The default statement should be written in the case. Okay, remember that one. And these are all the multiple operations we are going to perform. You can write your own operation, no problem. This is actually basic code. You can write your extra logics also by editing this code. And see, what are the outputs we have? Carry, 0, sign, parity we have. So for carry, no problem. So carry we are making, first of all we are initializing with 0, temp we are initializing with 0. So in the waveforms, if you don't initialize, we will get high impedances or unknown values. So that's why at 0 simulation time, to get values, initial values, we are making it with zeros or ones. You can initialize with any value and 0. So what operation? So they are writing small logics. If the output will get 0 0 means this 0 will becomes high. So we will get 0 as high only when output has 0 values. 4 bits are 0 means automatically 0 will be there, 0 will become high. And sign, for checking sign, we can write our own logics like this. This is a basic code. So see, now we will go for linear test bench. So see, whatever the inputs we are declaring here, that should be taken as reg in TB. Okay, you can use different names also. You can use different names here. Instead of A, we can use another name. But the next process will come. And outputs, see, you have all declared outputs here as reg, right? That should be declared as wire in the TB. Okay, because we are catching the outputs, we are catching the values from the outputs. They should be continuous driven. That's why we are declaring as y. And this is the main thing here happens. So see, here, let me explain with the diagram. So this is our RTL code. This is, let's take, this is TB. So this is RTL code. So both are different families. But if you want to test our RTL, that RTL should come inside of TB first. So that's process we will say it as instantiation. So we have to instantiate the design inside the TB, then we have to provide the inputs for the RTL, then that will produce the outputs as a waveforms, then we can analyze it. This is the process actually happening. So first of all we have to make that RTL come inside the TB, right? So that only we are doing here. See, in TB we are going to instantiate our design. So this is the module name of our RTL file, always com value. For that we have to give some instance name. So it can be any type, it can be any name, your own name also you can keep. And we have whatever we declared here in the TB, that should be allocated, that should be mapped to the inputs, whatever the inputs outputs here. So here we have A, B, selection Y, right? That should be mapped with the test bench variables. So this dot A represents this A, and whatever the A you are supplying here, that is this A. Okay, that is the difference. This mapping should happen. So there are two types of instantiation. So this line of code, we will call it as instantiation. There are two types of instantiation, name based and order based. So it is actually name based. Each name we are instantiating, each name we are making. So dot selection means RTL, and inside we are passing, this is related to the TB related things. So that is actually name based instantiation. So order based instantiation means like what, how it will look. Just check, that's a task for you. Just check what is order based instantiation and see. So before that you have to know the difference between what is actually, I think hope everyone know the difference. So what is actually always block and what's actually initial block? Where always will be used, where initial will be used. Always have arguments, like it has sensitivity list, whereas initial don't have sensitivity list. And always will perform continuously. It will always, like infinite times. There is whenever the input changes, it's keep on updating the outputs. So that like that always will perform. There is no end time. Like it will perform infinite times until we stop the simulation. It will perform, keep on the loop, iterate, keep on iterating based on the condition, based on the input changes. But initial is like different. It will execute only one time. Initial block will execute only one time, but always block will execute infinite times until we stop the simulation. And we have to know the forever loop also. See, what is forever? What is the difference between forever? Is also like it won't have an arguments, but forever also iterates infinite times. Always also have infinite times. But what's the difference between forever and always? So in always we have some conditions, we have some sensitivity list, but in the forever we don't have any sensitivity list. But both will execute, both will perform infinite operation only. So just know the difference between them. That only. So initial actually used for simulation purpose, whereas always will use it for synthesis as well as simulation purpose. Both it will be used. See, in initial block. So this block will execute only one time. So in test bench we have to use initial blocks only. Initial, begin, end. Since we have multiple statements, we have to use begin end block here. So they are using $display for just for our identification, and they are manually they are providing input, and after that they are giving some delay. So for A they are providing 5, B they are providing 3, selection they are giving 0, 0, 0. So they are providing manual inputs. So there are like this manually they are providing the inputs and selection. Based on that output will be generated automatically. We can observe in what? Through display statements you can observe. So if you give $display and in $display if you pass Y, you can see it in console, or else you can observe it in waveforms, anything. Like this they are manually providing the inputs, and after certain delay they are providing the new input again. So this is actually manually. So like this we have to write our own code more, so the length of the code is more. But if you go for test bench like task based or function based, maybe the code may be more, but it has more reusability. We can call this entire thing, we can keep it in a task, and we can call the task infinite times, how many times we want. That will go through. So this is the basic code. Then what's the process of execution? See, first thing we have to aware of selecting this one. We have to select this TB, and then we have to proceed here, run simulation. So run behavioral simulation we have to perform. First save this. Then automatically the simulation will start. The tool will generate the waveforms. See, if you get any errors like that, it will show. So launch simulation. So you can go down. This is the console. You can see any errors are there. If I can explain, you can get here. So go through the errors what you get. Just try to rectify them, like registers. If you are assigning always, if you are missing any semicolons, just go through them once again. So this is the console actually. You can see the errors here and we can analyze. So here see, this is the waveforms we are getting here. Just expand them and analyze them. So if you want to make your waveform compress, we have to use this keyword. This press, you just press on it, you will get like this. So if you want to change this system, binary numbers to any other system, just press on control and select each and everything, and just give right click, and here go to radix, and here you can change to octal hexadecimal for any. So if you are working with binary, you can easily understand if you get the binary values. So since we are declaring it as multiple bits, right? Here we are declaring it as vector, and we are passing the values in also like binary. You can easily to analyze in a binary only. So like this you can change the number systems also. So this is simple process of simulating the design, and we'll go for next test bench. So that is what task based test bench. So in task based test bench, as I said before, you can use the design, more reusability is there. See, and one more thing I want to say. So for commenting purpose, so if you don't want to include this inside simulation part, we will use like this, just double slash. So if you want to comment multiple lines, you will use this one, slash star, and at whatever the part you want to end with, slash star. Like this, multiple lines you can comment. That can't be included in our design. In RTL, if you want to do, means you can't, the lines can't be fabricated. So I want to comment this full test bench, and I will show the task based test bench. Just go down. Let me go open the task based test bench. Here the task based test bench actually. Let me copy the code. So in this task based test bench, almost every topic of the Verilog will be covered. Okay. After copying, just Control save. We have to save the file and expand it. Simply, as I said before, this is previous design. Okay, here we have to declare the module, and inside what are the inputs we have, we should declare it as reg, and output should declare as wire. And as you know very well, we have to instantiate the design, and we have to map every inputs and outputs. Then we are going for task. See, so we are write this. We have to write the task and end task. So we are giving some name for a task. See here, input is declared 3 bits, TA, TB and selection. So that input can be assigned to A. So whatever the input, whenever we are calling this task and we are passing some arguments, that values will be assigned to our AB here. Whatever we declared here, AB, right, that will be assigned to here, and this AB values will be assigned to the design again. Like this, the flow will take place from task to the inputs, like whatever the registers we declared inside our test bench, from the registers to the inputs what we have in the design. So then automatically design will get the inputs, automatically it will produce the output, like that. So this is actually small task. Coming to function, as I said before, without observing the simulation, we can say that output came perfectly or not. So for that we are using functions. So functions have return type. Return type is nothing but it will generate something just by calling this. So this is the function name, and for function we are giving again input, full adder, full var, like whatever, just give your own names, anything. So based on that F selection, if we are implementing, it will perform the again operation. So that operation is compared here. See, that just before these and all will be like what, tasks and functions can be defined outside the initial blocks. So in the initial blocks we are going to be in the actual operation actually happens here. Whatever the tasks we have declared above, what are the functions we declared above, that task and function should be called here in the initial begin. So see, here just display just for our formality purpose. Here using for loop. So what we are using, for I equal to 0, I less than. So for loop actually expects 3 arguments, just remember. So initialization and the condition and the incrementation. Increment or decrement, whatever you can use. So initialization, condition and increment or decrement. So like this, for I, j, k, they are declaring it as 3 integers, they are using here just for applying the inputs. So before code, if you go through means they are applying manually, but here loops will take that condition to apply the inputs. So that loop will iterate, start iteration. What is the initial value of 0? So based on I equal 0, this value get what? J will get 0, k will get 0. So first value will be apply input of 0, 0, 0. So this will go to upper task where apply input is there. So it will go to here. So 0, 0, 0. That will be allocated. Based on that, output will be generated, and we will get output as y. And like that, task will be executed. Coming to function, see, functions we are performing, like we can call it in if else loop also. So if y not equals to expected output, so expected output, if you came to know, that means if expected result is what, our function name. See, a function name. So this function, as I said before, it has some return type. Based on the inputs, it will generate the output here. So that output, that generated output is compared to the output generated by the RTL again. See, y is actually the what? It's the RTL, whatever the output is given by the RTL. But expected result is the output given by this function. Based on that, if it is not equal means it will show an error. If it's equal means we will get, yeah, the verification is successful, like that. So like that automation we are doing with tasks and functions. So this is a little bit complex code. There are so many easy codes you can use, you can work on it. Just take the help of the ChatGPT, learn as much as the codes you learn. So ask, I want a simple design. So I just want to learn tasks and functions with a simple design. Just ask it, it will give. And if you have any doubts, ask them in the next session. Like this, we will perform tasks and function based test bench verification. And that's it, guys. So like this, we are verifying Verilog based, like Verilog, up to Verilog, this type of test bench is enough. And one more thing. Tomorrow, wait guys, yeah. So tomorrow class, mostly there is no tomorrow class, like after 2 days we have again next session. So hope you are working on assignments as I given yesterday. Just try to complete assignments and try to upload by tomorrow end. And your today's class I given some tasks, try to work on the task and try to know what are the compiler directives also. So what are the compiler directives we have? What are the system tasks we have? Just go through in them. So just learn it perfectly. So in the next session we are going to discuss about sequential circuits, how actually they are fabricated. So what are the construct we have to implement for implementing sequential circuits and many more. That's it, guys, for today's session. If you have any doubts, you can ask or else you can leave. Thank you so much for joining.